I hope the rest you understand. We look at the imaginary part to tell if the circuit is inductive or capacitive. Now, since it has a positive reactance, the circuit it is inductive. Now, since you have this as your since you have this as your impedance. Now this can be represented in terms of the polar form, where with polar form, or let's say now, in terms of the rectangular form, where this 3 will lie on the x-axis. This will be positive 3 because this is where your real numbers are found on the horizontal axis, where now on the y-axis, where we refer this to imaginary axis, this is where we find our imaginary part, where in this case you have 7 because it's on the positive side. This will be on the upper side, on the 90-degree side. It will be 7J, and if this is 7J, it means this in terms of now calculating the hypotenuse side, we will say this is, can I have someone to admit the guys who are joining? Now this is at a length of 7. This is at a length of 7J, and this also is 3 units. Now to convert this to the polar form, we know that you have to do this. You have to, in terms of this, let me write this. How do we convert this to polar? Polar is when you have the magnitude at an angle of theta. At an angle of theta. This will be in polar form. Now, how do we get the R? The R, it is equals to the root. Now, I want to write what we already know. I will use the numbers as we have. 3 squared plus we have 7 here. It will be 7 squared, and this in terms of the magnitude, what will it give us? 7,616 ohms. All right, this is in ohms. And to determine now the current, no, the angle, we have what? We have the adjacent and we have the opposite, which is 7. Then we can use a trigonometric function which involves 2 of those parameters, adjacent and opposite, and that is tan theta, but we're looking for theta. Tan theta is equals to opposite, which is 7 divided by 3. And from this, it gives us our theta to be what? Talk to me.
66,8.
66,80. 80, let's say 01. Right now, this is the angle, meaning your rectangular form can be expressed in polar form as 7,66616 at an angle. Now, at an angle of 6,801. 801. Now, the angle now of the impedance, it is positive. Please take note of that. We'll explain what is this meaning. Is positive, and if we were now to calculate the current of this, the current, let's say now the voltage is given at 0 degrees. The voltage is given at 0 degrees, and you want to calculate the current. The current is V over Z, and our V is what? Let's say it's a certain number in volts, at an angle of 0 degrees, at an angle of 0. But that of the impedance, it is this, which is 7,66. Now this will give you an answer, a value of an impedance, a value of the current, pardon me, value of the current, and an angle of, now this will be 0 minus 66,081 equals to x at an angle of 66, negative because it's 0 minus 66, negative 0,801 degrees. Now this is our current, and we said at this instance, having the current now, the voltage at 0 and the current at negative 66,801, what do we say in terms of the current? Is it lagging or leading?
Leading, sir.
Leading. Why are you saying it's leading?
Lags the voltage by 90 degrees.
It lags. It lags the voltage by
It leads by 90, leads, sir.
All right. No, Mr. Nkosi, look now. You don't have 90 degrees. What we have is negative 66,801. It's negative, and that of the voltage is 0. This, it lags. It lags the voltage. What am I doing? It lags the voltage by negative 66, or by an angle of 66,801. I hope this is clear. I hope this is clear, guys. In this case, it lags because whenever the circuit is inductive, the current will lag. Whenever the circuit is inductive, the current will lag. Now, let's say you have, now we change, this is number, let's say now you have a Z being now, Z being, let's say 6 minus 3J, or let's say 4J, 5J. This is now 5J. Can we quickly convert this to polar form and get the magnitude and the angle? What are we getting as our polar form?
7.810 is the R. Is the magnitude.
Is that the magnitude, and the angle?
Angle is 39.805. No, 6 degrees.
39 is negative or positive?
Yeah, negative.
Negative 39,806. Now, let's say you have the same voltage. You have the same voltage. The current will be what in terms of the angle? The current will be positive. Do you agree with me? The angle of the current will be positive, and if the current angle of the current is positive, what we say the current it leads the voltage. The current it leads the voltage if the angle is at a positive. Now, because that of the voltage is at 0 and that of the current is at positive, now the current would lead. Now, it is of importance to calculate the voltages of these impedances, the current, the voltages of this, the impedance or the voltage across the components which are connected in the circuit can be inductor or the capacitor. Also, it is of importance to calculate the current, to be able to calculate the current flowing in the circuit and the powers. Now, I hope you have noted me saying powers instead of a power, unlike for a resistive circuit where we usually calculate the power in a resistor, a power in a circuit. Here we introduce now different powers which are flowing, pardon me, which are found in an AC circuit, where one of that is the apparent power. And we also have one which is referred to as real power or active, what am I doing now? Active power. Then we have another one which is referred to as a reactive power. But before we introduce this, let me do this. Let me draw in terms of the triangular form. Now, as we said, in terms of the horizontal line, when we represent this in terms of a triangle, you'll have on the horizontal line, you will have the R. This is where you find your R, your real part of the imaginary number. And on the horizontal line, we have our X. Our X, I'll explain the X and what's the difference. And we have on our hypotenuse the Z. Have the Z here on the hypotenuse. Now, having this, the angle can be calculated here. This is this angle which we calculated, which is using tan theta 66,801. Now, this is our triangle, but this XL, which this X, it will be on the top side of the polar diagram if the XL, let me write this, if the XL, it is greater than the XC. greater than the XC. If this is the case, we have this as our triangular diagram. But if we have now a different case where you have the XL now facing down. Now facing down. Remember, what do we have on the negative side of the we have negative J of the complex representation. We have negative J, and meaning we will have this as our hypotenuse. Then in this instant, you have resistor here. You have your resistor, and here you will have now, since it is here, let's say you'll have your Z, and in this side we have let me if you have this, you'll have XC being greater than XL. Let me highlight this so that it can be visible. You have X. Now, if XL, remember XL is accompanied by the positive J. That's why it will be facing up. The arrow is facing up because now this XL, because this now is the reactance. The reactance of the inductor is greater than the reactance of the capacitor. And if the reactance of the capacitor is greater than the reactance of the inductor, it will face on the negative side, indicating that it's on the negative side. And for this circuit, or for this phasor diagram, you have your circuit being capacitive, and this side you have your circuit being inductive. Now, the reactance of the reactance of the circuit is equals to, if you are told to calculate the reactance of the circuit, it is equals to the XL, this is the total reactance, is the reactance of the inductor minus the reactance of the capacitor. Reactance of the capacitor. This is our reactance. This is how we calculate the reactance. Now, having explained this, now let's start with our apparent power. The apparent power and the reactive power. The apparent power, which is, let me start with the real power. Let's start with the real power. Real power, which it is denoted by the symbol P. Symbol P, it is equals to, now let me first draw the triangular representation of the power in AC, where the triangular representation of the power, it is as follows, where you have real power, which will lie on the real part, because as the name, real power, real part, it will be here. And you have the reactive power, reactance. Reactive power, it will be on the horizontal, pardon, vertical. It will be on the vertical axis. Vertical axis. And we are left now with, let me do this. This is the reactive power. And you have the last one now, meaning it will be on the hypotenuse. And this is my S, which is the apparent power. Now, if we use the cos, because now we want to calculate P. We want to calculate P, and what trigonometric function can I use which involves P? We check cos, where cos theta, it is equals to the adjacent, which is our adjacent now is P, divided by the hypotenuse, which is S, and this, in making the P the subject of the formula, will have P being equals to S multiplied by the cos theta. Cos theta. And the units for power, this will be in red. The units for power is in watts. The unit for power is in watts. This is my real or active power. But the apparent power, which is represented by the letter S, it is equals to V times I. And the units, it is VA, which stands for voltage, volts amperes. Volts amperes. This is this will be highlighted to represent the units. Volts amperes. And if we have this as the formula to calculate the apparent power, it means the power, or the real power, is calculated by multiplying the voltage multiplied by the current multiplied by the cos theta. Multiplied by the cos theta. Now this is one formula which you can use to calculate power, one formula which you can use to calculate apparent power. Then looking now at this triangle, how do we calculate the reactive power? I will explain what is the reactive power, apparent power as we go on with the slides. Now, a trigonometric function which you can use to calculate which involves the reactive power is that of sine, where sine is equals to opposite, which is our Q, over the hypotenuse, which is S. And we make Q the subject of the formula. This, it means the reactive power is S multiplied by sine theta. But we are already aware that sine is V times I. Sine is V times I. And the units of this is VAR, where is volts amperes reactive, because it's the reactive power. It's the reactive power. The units for the reactive power is VAR. the units for real or active power, you can, whatever name you prefer, you can say reactive real power or active power, and the units is watts, and that of the apparent power, it is VA in terms of the units. Now looking at these equations or these triangles, we see that the power, it is on the real part where also resistor lies, meaning, or there's also another formula which you can use, which involves the resistor, but just for reminding you guys, remember power in terms of resistive circuit, we said power is equals to V times I, or you can say power is equals to V squared. Power is equals to V squared over R, or you can say power is equals to I squared multiplied by R. Do you remember this? All right, the people are quiet. All right, I hope we all remember this. Now, having this as now on our back of our minds, now it means power can also be calculated.
Sorry.
Yes, Mr.
The power, is it V squared over R or I squared?
The power is what?
The power, is it V squared over R?
Yes.
Oh, okay. I see now.
Yes,
Oh.
it is. Yes, it is.
Okay. Thank you, sir.
All right. Yeah. But now this is not the power for this, guys. I was just trying to remind you of these formulas. But we'll refer to these formulas when we want to get now the new or some other formulas which you can use when calculating the power. All right. Now, if we start with this one, the apparent power, let's start with the apparent power. Now with this, you have the voltage multiplied by the current, but the apparent power, it is on the hypotenuse. What do you have on this triangle? What do you have on the hypotenuse, guys? Guys, I'm listening. Okay, what do you have on the hypotenuse? You have the Z, meaning whenever we calculate the power, the apparent power, we have to involve what is found on the same side of the apparent power, which is the Z. Since we use this formula, it will be equals to V squared. And it will be wise of me if I indicate that this is the supply voltage, and supply voltage will be Vs. Also, this is the supply voltage. supply. All right. Now this is another formula to calculate when to be used when you want to calculate the apparent power. I hope you understand. We use the supply voltage squared over the impedance, because on the S hypotenuse we have this is representing the powers, and this is representing the impedance, the resistor, and the reactances of the circuit. And now, if we want to calculate that of the active power, using the same now V squared over something, what do we have on the where we find the active power for the impedance? We have resistor, meaning we divide here by R, and since the voltage which is across, if you have now a resistor, an inductor, and a capacitor connected in series, and you calculate their impedance or the impedance of the circuit, meaning it involves all those components connected in series and can be calculated, represented by one parameter, which is the impedance. And across that parameter, you will have the supply voltage. But if we separate those parameters, we'll have the resistor, the reactance of the inductor, the reactance of the capacitor, and the voltage across the resistor is not the supply voltage, but the voltage across the capacitor, the resistor, it is the portion from the supply voltage. Now we need to use the voltage across the resistor when we want to calculate the power using the resistor. Meaning I have to first calculate the voltage at the resistor, which will be represented by VR, and you square this. VR, and you square this. But remember, this is coming from apparent power, meaning this voltage, it is still the supply voltage. If I use this formula, you multiply the supply voltage with the current multiplied by the cos theta. But if I use the resistor, I will use the voltage across the resistor, squared divided by the resistance. I hope this is in order, or this is being understood. If it is, let's proceed. If we want to calculate the reactive power now, if we want to calculate the reactive power, it is using the same voltage, the same formula, the second one. Since we want to calculate the reactive power, we look what's on the reactive power. What's on the reactive power is the reactance. Remember, reactance is the total reactance of the circuit, which is XL minus XC. And this, since we will divide with the reactance because we are looking for the reactive power, and it means we will first need to calculate the voltage of the reactance, or across the reactance, squared divided by the reactance, where this reactance, it is the voltage across the capacitor and that of the inductor. Then you can calculate this, you can use this formula. Still this, the voltage, if we use this formula, V supply multiplied by the current multiplied by sine theta, to determine the reactance, or you can use V or cross the reactance, meaning the capacitor and the inductor, squared divided by the total reactance, where the total reactance is XL minus XC. It is not XC minus XL, but XL always XL minus XC. And this, it is in terms of using this the voltage or the resistor, the impedance and the reactance to calculate the power. And if we do this, it will surely give you the same answers. It will surely give you the same answers. And okay. Do we have any questions with regards to this, guys?
So what you just explained, can you please explain it again?
Okay, all right. Explain. You mean in terms of the voltage?
Yes, so the voltage across the capacitor and inductance. I didn't get that out.
Or
right?
the last part? Okay. Okay.
Yeah.
All right. Now let's say you have a circuit where there is a resistor, inductor, capacitor connected in series. Now the voltage across, let me write this, the voltage across the, let me write it before here. The voltage across let's say the total voltage across the reactance. Reactance, it means the total reactance, which includes the voltage across the capacitor and the inductor. You add the two since they are connected, if they are connected in series, it will be VL plus voltage across the capacitor. This is the voltage you will use when you calculate the reactance of the capacitor. Where the reactance, it is the reactance, this X, it is X is equals to XL XL minus XC. And we can use this formula by considering this to calculate the reactive power, or you can just say total reactance multiplied by the current multiplied by the sine theta to determine the reactive power, or you can use this formula. Are there any other questions? None. Okay. But the question might be that in terms of this angle, of this theta, which angle are we using? Looking now at this example where you have the impedance, which is 66,801, the current, which is negative 66,801, the voltage, which is at 0 degrees. We have three angles. Which one do we use when we calculate the active power or the reactive power? Because these angles for sine theta and this one for cos theta is the same. It will be the same angle, but it is wise to explain this in terms of the looking at what we have already solved. The angle that should be used when calculating the active power or reactive power is the angle between the voltage. It's the angle between the voltage minus the angle of the current, meaning the angle between the voltage and the current. Let's go back to okay, let me draw another one here. You have, let's draw a phasor diagram. Not this. Let me use a correct one. All right, then let's look. Let's say our current is 220 at an angle of 0. 220 at an angle of 0, meaning it will be here. This is where our current, our voltage is. This is our voltage at an angle of 0 degrees. Then our current is at negative 66. Negative 66. Let's say negative 66 is somewhere here. Let me use red. Okay, this represents our current. This is our current here. This is current. Look now. This is our current, and this is our voltage. This is our voltage here. This is our voltage. Now remember, the voltage is at our voltage is at 0 degrees, and our current is at negative 66. Negative 66,081. This is the angle. Now, what is the angle between these two? What is the angle between these two? Now, the angle between these two is 66,801. Meaning, where is it? Where did I write this? Yeah, there it is. To calculate this theta, which will be used when calculating the active power or the reactive power, it is the angle of the voltage, which is 0 minus 66,081. This is by looking at this example. Then our angle will be 66,801. This will be used when we have to calculate the power, the reactive, the real power and the reactive power. We'll use 66,801 because this angle always is the angle between the voltage, the supply voltage, and the current, the total current flowing in the circuit. Okay, but we also have another parameter which it needs to be explained, and that is power factor. Power factor. Power factor, which sometimes it is represented by PF, and this is by how do we determine or calculate the power factor? Power factor is cos theta. Cos theta, where the theta is the same theta which we just discussed now, which is the angle between the voltage and the supply voltage and that of the current, the supply current. This is the power factor. Why do we need to calculate this power factor? Power factor is just a representation of how a system converts the power input to the power out, meaning the consumed power to that of the total power. It usually represents, same as with the efficiency, it is the similar representation where it represents how how effective is the system in converting the input power to the output power. The more you have the losses, the more less the power factor it will be. The less you have the losses, the more effective the power the system will convert the power the input power to the power factor, the output power, which is the consumed power. Then this is represented by the power factor. Now looking at this, power factor is cos theta, and now cos theta, looking at this triangles, cos theta, it is, remember cos theta, how do you calculate cos theta in terms of trigonometric functions? It is adjacent over the hypotenuse, meaning we can calculate the power factor by dividing the power divided by the reactive power, or in this triangle we can say z over r over z. We can say r over z. Over z. Now these are some of the formulas which you can use to calculate the power factor. The power factor is very, very vital. I don't know how to emphasize this, but it's very vital. That is why I wanted us to go into the nitty-gritties on how you calculate the current, and why do we say it is lagging and why do we say it is leading. We look at the impedance. If the impedance it is positive angle and that of the voltage is 0, the current will be at a negative angle and the current is said to be lagging. If the impedance it is as the number 2, if the impedance angle is negative and that of the voltage it remains at 0, the current will be at a positive angle and the current will lead the voltage. Now this current, it assists us in determining if the current is lagging or leading. It assists us in determining if the power factor is lagging or it is leading. If the power factor if the current is lagging, the power factor will also lag. If the current is leading, the power factor will also lead. That's why I started by doing this. Then this, because now if you give me the answer of the power factor, let's say as 0.5, without stating if it is lagging or leading, that is a wrong answer. You need the power factor, it needs to be accompanied by the phrase lag or lead to state if it's lagging or it is leading. I hope this is clear, guys. Are there any questions?
Yes, sir.
Yes, Pale.
So, may I ask, which chapter are we going to use for this course? Because in my precepts textbook, you say chapter 8 and 9. So I don't know which chapter should I use. Chapter
Okay.
8 and 7. 8 and 7. Sorry.
Okay. What is? Can you just read the title of chapter 7?
Okay. Chapter 7, it says alternating voltage and current.
Okay. Chapter 8.
Okay. Pardon me. Let me check.
I think isn't it a single phase something?
Yeah, it's single phase series AC circuit.
Good. Yes, both those chapters.
Or both of them.
Yes, Mr.
Or I do everything in this.
Everything. That's why I said we will only cover series. Yeah, that's on the chapter 8.
Okay. Oh, chapter 8, 7 and 8.
Yes, 7 is an introduction to AC. Then 8 is now dealing with problems and solutions of series AC circuit.
Right. Right. And
Yeah.
then should I do? Are we gonna do even transformers?
Yes, yes, we will. But it's just an introduction of it.
All right. All right. I'll just read through all
Okay.
the textbook.
All right. All right. Are there any other questions with regards to this now? What we've just discussed in terms of calculating power, calculating the reactance, calculating the apparent power, the current, the power factor. Do I have any questions? All right.